In this chapter, we will look at classifying chemical compounds into two broad categories, those that are living and those that are not. As you've learned, compounds can be classified as ionic or covalent. These two categories of compounds are based on how they bond. We're going to look at how compounds can be categorized another way, and that is the two categories organic and inorganic. That's basing things, breaking them down into categories based on whether they come from living things or they're a component of living things, or whether they're not a component of living things. Organic compounds are compounds that are based on living things or come from living things, and they have a high percentage of carbon. So they have a high percentage of carbon, and that's determined by mass. So they have a high percentage of carbon by mass, and they must also contain hydrogen. Examples of organic compounds are things like sugar, methane, and vitamins. Inorganic compounds are compounds that have little or no carbon. So compounds that have little or no carbon. Examples are things like water, salt, carbon dioxide, etc. So we're going to make a little classification chart here. At the top is compounds. And compounds can be broken down into two different broad categories. Those that are non-living, so inorganic. And coming from living things, organic. Or you know what, actually I'm going to do this the other way around, so just erase this. I'm going to put organic over here. So I'm looking at the way the arrows go beneath. So organic, inorganic. Because all organic compounds are covalent, whereas inorganic compounds can be either covalent or ionic. In section 8.1, we're looking specifically at inorganic compounds. So we'll look at the two categories that fall underneath this. Inorganic molecular compounds have little or no carbon. They're molecular, so they have covalent bonds. And there aren't really a lot of these. Most inorganic compounds are ionic. So this means that they are made up of a metal and a non-metal. And these are all the ones that you've studied so far. So inorganic ionic compounds can be broken down into three more categories: acids, bases, and salts. So we're going to look individually at what makes each of those what they are. So an acid is something that releases hydrogen ions in solution. So you know that ionic compounds, when you put them into a solution, will break down into their ions. So it'll release H plus ions in solution. Acids have a sour taste. Acids conduct an electric current, just like all inorganic or ionic compounds do. So conduct an electric current. They react with metals, not with all metals, but with certain metals to produce hydrogen gas. So react with certain metals to produce, and hydrogen gas would be H2 gas. And they cause chemical indicators to change color. So I should put cause chemical indicators to change color. For example, if you put litmus paper in an acid, it'll turn red. Bases, on the other hand, don't release H plus ions, they release hydroxide ions. So release OH negative ions in solution. Bases are alkali. Bases are slippery and they're bitter. They also conduct an electric current. Again, just like all ionic compounds. Over the page, continuing on with bases. They do not react with metals to produce a hydrogen gas. So do not react with metals to produce H2 gas. And like acids, though, they cause chemical indicators to change color. So if you put litmus paper in a base, it'll turn blue, where in acid it turned red. Salts are the third category of ionic inorganic compounds, and they release positive and negative ions other than H plus and OH negative. So release positive and negative ions other than H plus and OH negative. So neither of those will be released when you're looking at salts. They do, though, conduct an electric current. They do not react with metals to produce hydrogen gas. And they have no effect on chemical indicators. So if you are using any chemical indicator, you will not be able to determine if it will just not have a change when you put it in a salt. So have no effect on chemical indicators. Okay, we're going to look at the concept of acidity, and we're just going to scroll down here to this table, table 4, classifying solutions as acidic, basic, or neutral. And we're going to be looking at the ion count to do this. So for something to be acidic, then there must be more H plus than there is OH negative. So more hydrogen ions than there are hydroxide. For something to be basic, it has to be the other way around. So the H plus ions have to be less than the hydroxide. For something to be neutral, then the hydrogen ions have to equal the hydroxide ions. So therefore acidity is really a measure of how much the relative quantities of H plus and OH there are in a solution. Chemists have a scale to measure acidity, and it's a log scale, and it's called the pH scale, and it goes from 0 to 14. And this is on page 205, so see page 205 of your textbook, and there's a more complete scale there. But just to put some things on, 0 to 14, so right in the middle would be 7, and that is where pure water would fall. Water is, and I'm just going to draw this up here, HOH. That's just another way of writing H2O, and HOH will break down into H plus and OH negative. So it has both H plus and OH ions, but it has equal numbers. It'll always break down into one H plus and one OH, so it'll come out completely neutral. For something to be less than 7, it is an acid. So going this way on the scale, is more acidic. Going this way is more basic, so the bases would fall over here. To put on some examples, at a pH of 1 is stomach acid. So the acid in your stomach has a pH of 1. And at about 10 is where we find most soaps. And again, on page 205 is a more complete scale with more examples all along that. The next thing we're going to look at in 8.1 in this section is naming acids. So to do this, what you need to do is look at the formula. And we're going to create a little flow chart based on the formulas. So you will examine the formula. And so here are some examples and formulas. You can look at those. And the first question you need to ask yourself is, does it contain oxygen? Does it contain oxygen? From here, we're going to branch off either yes or no. If it does contain oxygen, the situation can be a bit, I don't want to say complicated, but there's two different choices. It will either have an 8 ion or an ite ion. So you need to look up the ion and see what its name is. So for example, if we had HNO3, this is nitrate. So it's an 8 ion. So this would be hydrogen nitrate. But that's just its ionic name. That's not changing it to its acidic name, which is what you have to do now. So what you do is you drop the hydrogen from the name, and you change the ending from 8 to ic. So it becomes nitric acid. If it was an ite ion, like chlorite, so HClO2, so this would have been hydrogen chlorite. You again drop the hydrogen from the name, and this time you change ite to us. So this becomes chlorous acid. If something does not contain oxygen, if you went down the no path, then it ends in ide, so like HCl, hydrogen chloride. So that would have been hydrogen chloride. It instead becomes hydrochloric acid. So you keep the hydrogen, change it to hydrochloric acid. When you're naming bases and salts, it follows the same rules that you learned in chapter 7.